Hi, welcome to Aero 23's wing design activity. In this project, we aim to design a wing structure that will meet preset requirements, follow the design process in order to create a system that will minimize total mass. Working under the assumption that the spar is taking all the stress and the rest of the structure is just there for shape, the most important factor to lower the stress is increasing the height. Now that could only be done up to a point of 47 millimeters due to the constraints from the size of the rib. There were two approaches we looked into for cross-sectional design. The first one was a relatively narrow width, obviously again maximum height, but relatively high thicknesses, and then a taper that would reduce the thicknesses as the length increased. Option B, again maximum height, but this time we're going to make it very, very wide and very, very thin, both top and the sides. Whilst both options fit the analytical criteria and option B had a much lower mass for constant cross-section area, we went for option A as there was greater flexibility when it came to tapering, so we felt overall mass would be reduced. We looked at three types of tapers: internal, external horizontal, and external vertical. But we concluded on internal because it maintains the biggest stress reducers, height, and to a lesser degree width, maximizing our mass reduction. Ideally, considering a linear stress distribution, the tape would have looked like this. However, due to material constraints, i.e. that we're dealing with boards a minimum of 5 millimeters thick, this could not work. We also encountered problems in high-resolution testing due to this discrepancy between the analytical Excel and the practical side of SolidWorks. We're also having a problem with the height of the spar fitting into the rib with areas sticking out. In order to resolve these problems, we decided to build our spar in horizontal 5 millimeter thick layers, which would allow us to now taper and step our spar. There was again a discrepancy between SolidWorks and Excel with the necessary width criteria, where Excel only required 40, the SolidWorks required 42. Interestingly, although the linear stress gradient would have suggested that the step should have made 200 millimeters from the tip, due to the fact that there were concentrated stresses in the far corners near the root, and the linear stress gradient only began further forward, it's actually allowed us to take that step at 500 millimeters in, really reducing mass greatly. Unfortunately, the displacement test was a failure. While load factor 1 allowed 15 millimeters and a load factor 2 should allow 30 millimeters, we were hitting 33. We had two options to solve this. The first one was to reduce the step to 300 millimeters, but that would greatly increase the mass. Option 2 was to merge earlier options A and B together to give a very thin-walled and wider spar. This now satisfied all of the above criteria: stress, torque, and displacement, generating our final and most mass-efficient spar design. Using the Excel tool, we generated a sketch of the aerofoil to be used for the rib. As mentioned earlier, the ribs only existed to shape the skin, so all areas that weren't in the outlying areas were removed. Although our analysis suggested that only 2 ribs would be necessary, we decided to add a third to reduce the chances of sagging. We then put together our final assembly, including the leading and trailing edges, again composed of 5 millimeter thick layers of foam board. Thank you very much for watching. Any questions?